Picture for a moment the most perfect darkness imaginable. Not the simple dark of a moonless night, but an absolute, voracious void where the very laws of physics as we know them cease to exist. A place where gravity is so intense that not even light can escape its grasp, where time itself is stretched and warped beyond recognition. This is the realm of the black hole, the universe's most enigmatic and terrifying phenomenon. For decades, they have existed in our textbooks and our imaginations as the ultimate endpoint, the cosmic vacuum cleaners from which nothing returns. But what if that classic image, that singular idea of destruction, is only a fraction of the truth? What if black holes are not just simple holes in spacetime, but something far more complex, more bizarre, and more fundamental to the fabric of reality than we ever dared to dream? Today, we are going to venture beyond the event horizon of established science and into the thrilling, speculative frontier of theoretical astrophysics. We are not abandoning science, we are following it to its most logical and often its most unbelievable conclusions. The theories we are about to explore are not wild fantasy. They are ideas born from complex mathematics, cutting-edge observations, and the brilliant minds of physicists who are willing to ask the biggest questions. They are the what-if scenarios that could, with just one new piece of evidence, reshape our entire understanding of the cosmos. This is a journey into the realm of possibility, where the rules are being rewritten and our universe is revealed to be stranger and more wonderful than we ever thought possible. So prepare to have your mind expanded. We are about to dive deep into 25 astonishing theories about black holes that, against all odds, could very well be true. From the idea that they might be gateways to other universes, to the possibility that they contain entire worlds within their mysterious interiors, to the shocking notion that they could be the key to understanding the origin of everything. This is not just a list of facts, it is an invitation to explore the very edges of human knowledge, to stand at the precipice of the unknown and peer into the darkness. What we find there might just change everything. Let's begin our exploration with a theory that strikes at the very heart of what we think a black hole is. For generations, the textbook description has included a terrifying finality, the singularity. This is the hypothetical point at the very center, hidden behind the event horizon, where all the matter that ever fell in is crushed into an infinitely dense, infinitely small point. Here, the equations of general relativity break down completely, and the fabric of spacetime itself is thought to be torn apart. It's a concept that has fueled scientific and philosophical debates for decades, a place where physics as we know it simply gives up. But what if this ultimate endpoint, this cosmic divide by zero error, doesn't actually exist? A growing number of physicists now suspect that the singularity is merely a placeholder, a sign that we're missing a crucial piece of the puzzle, the laws of quantum gravity. This is where two fascinating alternatives enter the picture. First, consider the Planck star. This theory suggests that instead of collapsing forever into an infinitely small point, the dying star's core reaches a state of maximum possible density, governed by the quantum nature of gravity itself. Imagine compressing a spring. You can push it down, but eventually it will resist with immense force. In a similar way, when matter inside a black hole is compressed to the unfathomable density of the Planck scale, the smallest possible unit in the universe, a powerful repulsive force from quantum gravity is theorized to kick in. This wouldn't be a gentle bounce, but a moment of cosmic stalemate. The collapse halts, creating a tiny, absurdly dense object that is not infinitely small, but is instead stabilized by these fundamental quantum pressures. From our perspective outside the black hole, this process would be frozen in time due to the extreme gravity, meaning the Planck star exists in a kind of eternal, suspended animation at the very core. Then there is the even more exotic gravastar, short for gravitational vacuum star. This model proposes that black holes are not hollow pits leading to a point, but are instead filled with a bizarre form of energy often compared to the dark energy that is accelerating the expansion of our entire universe. In this vision, the event horizon is not a point of no return, but a thin, incredibly durable shell made of an exotic form of matter. Inside this shell, the immense gravitational energy of the collapse has been transformed, creating a bubble of this repulsive dark energy. It would be like a cosmic egg, a hard quantum mechanical shell containing a universe of negative pressure within. A gravastar would look almost identical to a classic black hole from the outside, warping spacetime and trapping light, but its interior would be a completely different reality, devoid of any central singularity. The implications of these ideas are profound, especially for the infamous black hole information paradox. This puzzle asks what happens to the information, the unique quantum identity of every particle that falls into a black hole. If it's truly lost forever in a singularity, it violates a fundamental law of quantum mechanics. But if the singularity is replaced by a Planck star or a gravastar, the information isn't necessarily destroyed. It could be preserved, scrambled across the surface of the object, or even eventually released back into the universe over astronomical timescales. Removing the singularity doesn't just clean up a mathematical anomaly. It could be the key to preserving the logical consistency of the universe itself, suggesting that even in its most extreme environments, nature abhors true infinities and always finds a way to uphold its deepest laws. Building directly on that idea of a singularity-free interior, we venture into a theory that reimagines the entire life cycle of a black hole, suggesting it's not an end at all, but merely one half of a cosmic circuit. If a black hole represents the ultimate drain, a point of no return where everything vanishes, then a white hole would be its perfect opposite, a cosmic fountain from which energy and matter can only emerge, never enter. The mathematics of general relativity doesn't just allow for such an object. Its equations are surprisingly symmetrical, and a white hole appears as a perfectly valid, if exotic, solution. So, if black holes exist, could their theoretical twins be out there somewhere? One compelling framework links these two objects together through the fabric of spacetime itself. Imagine the intense gravitational collapse of a black hole not as a journey to a dead end, but as a passage through a tunnel forged in the extreme warping of space and time. This is the essence of an Einstein-Rosen bridge, more popularly known as a wormhole. In this model, the black hole is one mouth of the tunnel, the point of ingestion. The white hole is the other mouth, the point of expulsion. Matter and energy that cross the event horizon of the black hole wouldn't be crushed into oblivion at a singularity. Instead, they would be funneled through this bridge and violently ejected from the white hole into another location. This could be a distant region of our own universe, or something far more staggering, an entirely different universe altogether. In this view, a black hole isn't a cosmic trash compactor. It's a gateway, a recycler on the grandest of scales. However, the existence of such a white hole presents a monumental problem for physics. It seems to violate the second law of thermodynamics, which governs the flow of order and disorder, or entropy. Our universe consistently moves from a state of order to disorder. A white hole, by spewing out pristine, organized energy and matter without any apparent source of input, would essentially be acting like a machine that decreases entropy all on its own, which is a fundamental no-go in our understanding of cosmic mechanics. This is a primary reason why most physicists consider classical white holes as permanent structures to be highly unlikely. But what if they aren't permanent? A more modern and radical take suggests that a white hole isn't a separate object at all, but rather the final fate of every black hole. This idea stems from theories of quantum gravity, which attempt to bridge the gap between general relativity and quantum mechanics. In this scenario, after a black hole has evaporated over trillions of years through the slow trickle of Hawking radiation, the final moment of its disappearance might not be a silent pop. Instead, the remnant, no longer able to sustain its immense gravitational grip, could undergo a quantum bounce, transforming into a short-lived white hole that releases the final burst of its stored energy and information back into the cosmos. This would be a spectacular, fleeting event, the black hole's last act of cosmic restitution. The challenge, of course, is observation. A primordial white hole born in the early universe would have likely expelled all its energy eons ago. And a white hole that is the end stage of a black hole's life would occur on timescales so vast that the universe itself is far too young to have produced one naturally. Any we might hope to see would be the rare, ancient relics of the Big Bang, and distinguishing their theoretical outburst of energy from a supernova or a gamma-ray burst is a problem we have yet to solve. So for now, white holes remain a beautiful, mathematically elegant possibility, a testament to the fact that for every profound ending our universe seems to offer, there might just be an equally astonishing new beginning waiting in the equations. Now, if a black hole can be a gateway and its interior might lack a destructive singularity, we are led to a theory of such grand, breathtaking scale that it redefines our very place in the cosmos. What if every black hole is not just an object within a universe, but is in fact the seed for an entirely new universe of its own? This is the core of the cosmogonic theory, a bold idea suggesting that our entire cosmic home, with all its hundreds of billions of galaxies, may have been born from a black hole in a vast, pre-existing parent universe. It's a concept that transforms black holes from cosmic tombstones into cosmic wombs. This idea is formally known as the fecund universe theory, proposed by physicist Lee Smolin, and it paints a picture of a regenerating multiverse governed by a kind of cosmic natural selection. The process begins inside a black hole. Recall that our current physics breaks down at the hypothetical singularity, but what if that breakdown isn't an end but a transformation? The theory proposes that the conditions at the core of a black hole, the immense density, the warping of spacetime to an extreme, are precisely the conditions needed to trigger a new Big Bang. In this scenario, the singularity doesn't form. Instead, the collapsing matter and energy reach a point of maximum compression and then bounce, rebounding in an explosive event that births a new spacetime continuum, completely disconnected from our own. From the outside, we just see a black hole, but on the inside, an entire new universe is flaring into existence with its own dimensions, physical laws, and potentially its own future black holes. This leads to a staggering implication, a form of cosmic evolution. Each of these baby universes would inherit its fundamental physical constants like the strength of gravity or the mass of an electron from the parent universe, but with the potential for slight, random variations. Think of it like genetic mutation. A universe that produces many black holes would, by this theory, produce many offspring universes. Over countless cycles, the multiverse would become populated with universes whose physical laws are fine-tuned for one primary purpose: to create stars, galaxies, and the conditions necessary to form more black holes. This offers a potential, non-theological explanation for one of the most profound mysteries in science: why our universe seems so perfectly fine-tuned for life. The constants of nature appear to be set with incredible precision, as if dialed to exactly the right values to allow for the formation of complex matter. If we live in a universe that is exceptionally good at making black holes, then those same conditions, the right strength of nuclear forces, the correct balance of elemental particles, might also be the very same conditions that inadvertently allow for the emergence of stars, planets, and life. We wouldn't be in a special universe designed for us. We would be in a universe that is highly proficient at cosmic reproduction, and we are simply a byproduct of that successful recipe. This vision creates a multiverse that is not just a static collection of alternate realities, but a dynamic, evolving ecosystem. It suggests a grand, cyclical process where universes beget universes, with black holes serving as the reproductive organs of the cosmos. While this theory is currently far beyond our capacity to test directly, it provides a powerful and elegant framework that connects the very large with the very small, suggesting that the key to understanding our own cosmic origins might lie in studying the most mysterious objects our universe has to offer. But if black holes can create new universes, we must also confront a theory that suggests they are not permanent fixtures of the cosmos, but are instead slowly, inexorably evaporating into nothingness. This brings us to one of the most profound discoveries in theoretical physics, a concept that forever linked the worlds of quantum mechanics and gravity: Hawking radiation. For centuries, the defining feature of a black hole was its absolute blackness. It was a one-way street where matter and energy went in, but nothing, not even a single photon, could ever come out. That all changed in the 1970s when Stephen Hawking performed a breathtaking intellectual feat. He asked a simple yet revolutionary question: what happens when you apply the strange rules of quantum mechanics to the curved space just outside a black hole's event horizon? The answer lies in the chaotic, frothing nature of empty space itself. According to quantum theory, a perfect vacuum isn't really empty. It's a seething sea of virtual particles. These are particle-antiparticle pairs that spontaneously pop into existence out of the sheer energy of the quantum fields, borrowing energy from the universe for an impossibly brief moment before they collide and annihilate each other, paying back the energy loan. This happens everywhere, all the time, and usually the effect is undetectable. But place this quantum frenzy at the precipice of a black hole, and something extraordinary occurs. Hawking realized that if one of these particle pairs appears right at the edge of the event horizon, the immense gravitational pull can tear them apart before they have a chance to annihilate. In this cosmic robbery, one particle falls into the black hole, while its partner is gifted with enough energy to escape into space, becoming a real particle. This is where the magic and the paradox truly begins. The escaping particle carries positive energy away from the black hole. To conserve energy, the particle that fell in must have negative energy relative to the outside universe. And when you add negative energy to a system, you subtract from its total mass. So every time one of these virtual pairs is ripped apart and a particle escapes, the black hole loses an infinitesimal amount of its mass. It's not emitting radiation from within its depths, it's creating radiation at its boundary and paying for it with its own gravitational mass. This is Hawking radiation, a faint, theoretical glow that should be emanating from every black hole in the universe. For a massive black hole, this process is incredibly slow. A black hole with the mass of our Sun would take trillions upon trillions of years to evaporate any noticeable amount. The cosmic background radiation bathing the universe is actually feeding it more energy than it loses. But in the far, far future, as the universe cools and expands, this slow leak will become the dominant process. And this leads to the truly explosive finale. As a black hole loses mass, it also shrinks in size. Its event horizon gets smaller, but the rate of Hawking radiation is inversely proportional to the black hole's size. The smaller it gets, the hotter it becomes, and the faster it radiates. This creates a runaway feedback loop. In its final moments, a black hole wouldn't just fade away quietly. It would be radiating away its remaining mass at an ever-increasing, feverish pitch. The final second of its multi-trillion-year life would be a cataclysmic burst of energy, releasing the equivalent of millions of 1 megaton nuclear bombs in a flash of high-energy particles and radiation. It would be the black hole's last stand, a violent shout into the void before it winks out of existence entirely. The quest to find evidence for this is one of the great challenges of modern astrophysics. Detecting the Hawking radiation from a typical stellar or supermassive black hole is currently impossible. It is utterly drowned out by other cosmic signals. So, scientists have gotten creative. Some are looking for the final, explosive moments of tiny, primordial black holes that could have formed in the dense early universe. These smaller black holes would be reaching the end of their lives right now, and their death throes might be visible as a specific type of intense gamma-ray burst. Others are attempting to recreate the conditions of a black hole's event horizon in the laboratory using sophisticated analog systems, like flowing water or structured light, where similar particle pair production can be studied. Finding any confirmation of Hawking's prediction would be a monumental triumph, solidifying our understanding of how gravity and quantum physics intertwine at the very edge of reality. It would confirm that even the most dominant forces in the cosmos are subject to the subtle, relentless ticking of quantum time. This brings us to a mystery so deep that it pits the two pillars of modern physics against each other in a fundamental conflict, a puzzle known as the black hole information paradox. At its heart, this isn't just a debate about black holes. It's a battle for the soul of physics itself, questioning whether the universe operates on logical, predictable rules or if true chaos can reign in its most extreme corners. The conflict is stark. On one side, we have quantum mechanics, the rulebook for the very small. One of its most sacred principles is unitarity, the idea that information about the state of a system can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must in principle be recoverable. Think of it like burning a book. The paper turns to ash and smoke, a seemingly irreversible loss. But a hypothetical, all-knowing physicist could, in theory, collect every particle of ash and wisp of smoke, trace the heat and light emitted, and perfectly reconstruct the original book. The information still exists, just in a vastly more complicated form. On the other side stands general relativity, which, when describing a classic black hole with a singularity, presents a very different outcome. When an object, be it a star, a spaceship, or that same book, falls into a black hole, general relativity suggests it is utterly annihilated at the central singularity. The unique quantum information that defined that object, the specific arrangement of particles that made it what it was, is erased from existence. According to this view, the black hole doesn't just burn the book, it incinerates it in a furnace of infinite density from which no evidence can ever escape. This creates an irreconcilable contradiction. Either quantum mechanics is wrong and information can be permanently lost, or general relativity is incomplete and fails to describe what truly happens inside a black hole. For decades, Stephen Hawking himself believed information was lost, famously making a bet against fellow physicist John Preskill, a bet he would later concede was a mistake. The search for a solution has spawned some of the most mind-bending ideas in theoretical physics. One of the most radical is the concept of a black hole firewall. If information must be preserved, and if it is somehow encoded in the Hawking radiation being emitted from the event horizon, then a strange consequence emerges. To ensure the radiation outside the black hole carries a perfect record of what fell in, the entanglement connections between the escaping particles and their partners that fell inward must be broken. This severing of quantum links would release an immense amount of energy, effectively creating a wall of blazing, high-energy particles right at the event horizon. This isn't the gentle point of no return from general relativity. It's a destructive inferno that would incinerate anything crossing the threshold. The firewall paradox replaces one problem with another. It saves information from being lost, but it violently violates the core principle of general relativity that an observer falling into a black hole should notice nothing special as they cross the event horizon. You'd be vaporized long before you reached the interior, turning the black hole from a graceful spacetime curve into a cosmic kill zone. A more elegant and perhaps less violent solution comes from the holographic principle. This extraordinary idea suggests that all the information about everything that has ever fallen into a black hole is not lost inside its three-dimensional volume, but is instead encoded on its two-dimensional event horizon, like a cosmic fingerprint smeared across the surface. Imagine taking that entire book and using an incredibly complex code, printing all of its information onto the flat surface of a credit card. The holographic principle proposes that the event horizon acts as this storage device, a vast pixelated screen where the quantum bits of information for every atom, every particle are stored. As matter falls in, it doesn't vanish, it simply adds its data to this sprawling celestial hard drive. The three-dimensional interior we imagine is in fact a projection of this two-dimensional information stored on the boundary, much like a hologram, which is a three-dimensional image projected from a two-dimensional film. This would mean that the information never actually enters a place where it could be destroyed by a singularity. It remains forever imprinted on the surface, potentially retrievable from the Hawking radiation, which carries traces of that surface data away over eons. This leads to the final piece of the puzzle, the radiation itself. Perhaps the information isn't just stored statically on the horizon, but is slowly and meticulously leaked back into the universe through the Hawking radiation process. The escaping particles wouldn't be random. They would be subtly imprinted with the information about what fell in, like a slow, cosmic broadcast of the black hole's entire history. The process would be incredibly complex, effectively scrambling the information into a form that would only make sense if you could collect every single particle of Hawking radiation the black hole ever emitted. It would be the ultimate jigsaw puzzle, requiring a godlike patience to piece together. But in principle, the story of everything that was ever consumed would be preserved in that faint quantum whisper. Resolving this paradox is not merely an academic exercise, it is the essential stepping stone to a unified theory of quantum gravity. The place where the paradox occurs, the event horizon, is precisely the point where the smooth, geometric world of general relativity meets the fuzzy, probabilistic world of quantum mechanics. To understand what truly happens there, we need a theory that can describe both. By forcing physicists to find a way to preserve information, the paradox acts as a brutal guide, showing us which ideas are viable and which are not. Any candidate for a theory of everything, from string theory to loop quantum gravity, must be able to solve the information paradox. It is the universe's way of testing our deepest ideas, ensuring that our final picture of reality is not just mathematically beautiful, but logically consistent from the smallest particle to the most massive black hole. This notion of a black hole as a gateway rather than a grave leads us directly to one of the most thrilling and iconic concepts in all of theoretical physics, the idea that hidden within the heart of certain black holes could be a traversable wormhole, a cosmic shortcut connecting two distant points in space and time. We've already touched on the classic Einstein-Rosen bridge, but it's crucial to understand why that original model is not a ticket to the stars. The bridge predicted by Einstein and Rosen was a direct consequence of the mathematics describing a simple, non-rotating black hole. It was a moment of profound connection, but it was a connection that was fundamentally unstable. This tunnel through spacetime would form and then pinch off into a new singularity, all in an instant far shorter than any conceivable timescale for an object to pass through. It was a beautiful mathematical possibility, but a physical impossibility for travel, a doorway that slams shut before you can even take a step across the threshold. But what if we could prop that door open? This is where the concept of a traversable wormhole enters the scene, moving from a mathematical curiosity to a hypothetical engine for interstellar travel. For a wormhole to be stable enough for anything to pass through it, the fabric of the tunnel, or the throat, must be kept from collapsing. The equations of general relativity show us that to achieve this, the throat would need to be lined with a truly bizarre substance, exotic matter. This isn't just matter that's strange or unknown, it's matter that possesses a negative energy density, imagine a material that, in a gravitational field, would fall up instead of down. This exotic matter would exert a kind of negative pressure, effectively pushing the walls of the wormhole apart and preventing it from catastrophically collapsing into a singularity. While this sounds like pure fantasy, hints of such negative energy densities do appear in certain quantum field effects, like the Casimir effect, where closely spaced metal plates in a vacuum can create a region with less energy than the surrounding space. The catch is that the amounts of exotic matter required to stabilize a wormhole large enough for a spaceship are astronomical, far beyond anything we can currently conceive of creating or finding. The possibilities that such a stable wormhole would unlock are the stuff of science fiction for a very good reason. A traversable wormhole would not merely be a tunnel through space, but a tunnel through spacetime itself. Enter one mouth near Earth, take a short stroll through the tunnel, and you could emerge from the other mouth not just in another galaxy, but in another time. It could function as a time machine, with the relative motion and gravitational time dilation of the two mouths creating closed time-like curves, allowing for travel into the past. For interstellar travel, it would render the vast distances of our galaxy moot. A journey that would take tens of thousands of years at near light speed could become a trip of mere minutes or hours. It would transform the cosmos from an impossibly vast expanse into a connected neighborhood. Yet, the challenges are as immense as the potential is grand. First, you would need to find or create a suitable black hole that doesn't possess a destructive singularity, but rather contains this stable wormhole interior, a property that is not predicted for the black holes we observe in nature. Then, you would have to figure out how to move one of the mouths. To make the wormhole useful, you would need to transport one end to a distant star, which would require moving an object with the mass and gravitational pull of a black hole across the galaxy, a feat of engineering that defies imagination. Furthermore, the very act of trying to pass through the wormhole could be fatal. Even if stabilized, the intense tidal forces, the difference in gravity between your head and your feet within the throat could spaghettify any object, and the potential for unpredictable quantum effects or instabilities makes the journey a monumental risk. So, while the mathematics of general relativity does not forbid the existence of traversable wormholes, it places them firmly in the realm of profound speculation. They are a testament to the power of our equations to reveal possibilities that are breathtaking in their scope, while also highlighting the vast gulf between mathematical possibility and physical reality. They serve as a brilliant playground for theoretical physicists, pushing our understanding of quantum gravity and the fundamental structure of spacetime, and they will likely remain one of the most compelling what-if scenarios, a dream of connection written in the language of the cosmos itself. Our journey now takes us from the depths of singularities and wormholes to one of the most pressing mysteries in all of modern cosmology, the enigma of dark matter. We know it's out there. Its gravitational pull is the invisible hand that sculpts the rotation of galaxies and binds clusters together, a cosmic ghost that makes up roughly 85% of all the matter in the universe. Yet, for decades, its true identity has eluded us. What if the answer isn't a new, exotic subatomic particle, but something we've been studying all along? What if dark matter is, in fact, made of black holes, not the giant stellar mass ones we find in binary systems, but a vast, unseen population of tiny, ancient black holes that have been drifting through the darkness since the dawn of time? This is the compelling premise behind the idea of primordial black holes. Unlike their stellar relatives, which form from the collapse of massive stars, primordial black holes are thought to have been forged in the extreme density and pressure of the universe's first moments. In that seething, hot soup of the early cosmos, random fluctuations in density could have been so intense that pockets of space simply collapsed under their own weight, pinching off into black holes of almost any size. This theory, first proposed by Stephen Hawking and others in the 1970s, suggests a cosmic population ranging from the microscopic to the supermassive, all born not from dying stars, but from the raw energy of creation itself. For this theory to explain dark matter, we need to focus on a specific mass range. If these primordial black holes were too small, say less massive than a large asteroid, they would have evaporated away by now due to Hawking radiation, their lives cut short in a flash of gamma rays. If they were too large, with the mass of a star or more, their gravitational influence would be too obvious. We would see them warping the light from distant stars and disrupting binary systems far more often than we do. The sweet spot, the candidate for a dark matter constituent, lies with objects that have come to be known as massive astrophysical compact halo objects. These would be black holes with masses comparable to a large planet or even a small star, dense enough to be black holes, yet small and dark enough to have remained virtually invisible across cosmic history. A galaxy like our Milky Way would be surrounded by a vast spherical halo containing trillions of these faint, drifting shadows, their collective gravity explaining the rapid orbits of stars in the galactic outskirts without the need for any undiscovered particles. The hunt for these elusive objects has been underway for decades, employing a clever astronomical technique known as gravitational microlensing. The principle is elegant. If one of these primordial black holes drifts precisely between Earth and a distant background star, its gravity will act as a temporary lens. It will bend and focus the light from that star, causing it to brighten noticeably for a period of time. The duration of this brightening is the key clue. It tells us the mass of the object doing the lensing. A planet-mass object might cause a star to brighten for a few hours, while a black hole with the mass of our Sun could create a microlensing event that lasts for weeks. Major surveys like the MACHO project and the optical gravitational lensing experiment spent years monitoring millions of stars in the Large Magellanic Cloud, our galactic neighbor, hoping to catch the telltale flicker of these dark halo objects. Their results were tantalizing but ultimately inconclusive. They found some microlensing events suggesting there could be a population of MACHO in our halo, but not nearly enough to account for all the dark matter. The majority of the dark halo, it seemed, remained unexplained. So why has this theory seen a dramatic resurgence in recent years? Two major developments have breathed new life into the idea. The first was the historic detection of gravitational waves in 2015 by LIGO, the Laser Interferometer Gravitational Wave Observatory. The signal came from the merger of two black holes, each about 30 times the mass of our Sun. This was a surprise. Stellar evolution models didn't readily predict the formation of black holes quite that heavy. The possibility that these could be primordial black holes, ancient relics from the universe's infancy, immediately captured the imagination of cosmologists. If such objects are common, they could represent a previously unseen population that contributes significantly to the dark matter budget. The second development is the ongoing refinement of microlensing surveys. While past searches focused on our galactic halo, new and more sensitive projects are casting a wider net. The Subaru Hyper Subprime Cam in Japan, for instance, is capable of detecting microlensing events caused by objects with masses as small as the Moon, surveying vast areas of the sky with unprecedented precision. If a substantial population of planet or asteroid mass primordial black holes exists, these observatories have the potential to find them. Furthermore, astronomers are looking for other subtle signatures, such as the effect these black holes would have on the cosmic microwave background radiation, or the way they might disrupt delicate structures like wide binary star systems. Confirming that primordial black holes are the dark matter would be a cosmological revolution of the highest order. It would mean that one of the greatest mysteries in science has been hiding in plain sight, its solution rooted in the gravity of Einstein rather than the particle zoo of the Standard Model. It would connect the largest scales of the cosmos, the distribution of galaxies, to the most extreme objects born from the Big Bang itself. The implications for astrophysics would be profound, reshaping our understanding of the early universe and providing a natural, gravitational explanation for a problem that has long been the domain of particle physics. The dark universe would suddenly become a little less mysterious, populated not by invisible particles, but by the countless quiet ghosts of creation. For decades, our understanding of black holes has been governed by a powerful, almost minimalist principle known as the no-hair theorem. In the pristine world of classical general relativity, this theorem asserts that a black hole is the simplest object in the universe. No matter how complex the star that collapsed to form it, no matter what intricate structures, mountains, or chemical compositions it once possessed, all of that complexity is irrevocably lost when the event horizon forms. The resulting black hole is stripped down to just three, and only three, defining properties: its mass, its electric charge, and its spin. That's it. Everything else, every unique detail about the matter that fell in, is completely erased, swallowed by the singularity. It's as if the universe takes a fantastically complex sculpture, melts it down, and gives you a perfectly smooth, featureless ball, telling you that its entire identity is now defined by just how heavy it is, whether it's spinning, and if it holds an electric charge. This elegant simplicity is why physicists say black holes have no hair, no individual distinguishing features beyond those three numbers. But what if this cosmic barbershop isn't as thorough as we thought? The no-hair theorem is a product of classical physics, a world without the fuzzy, probabilistic rules of quantum mechanics. When we bring quantum fields into the picture, the situation becomes far more interesting. Recent theoretical work has begun to challenge this decades-old doctrine, proposing that black holes might in fact possess a kind of quantum hair. This isn't hair in the literal sense, of course, but a metaphor for subtle, additional structures imprinted on the gravitational field surrounding the black hole. These structures would be woven from the complex interactions between the black hole's gravity and the quantum fields that permeate all of space. Imagine a black hole not as a perfectly smooth marble, but as an object surrounded by a persistent, intricate pattern in the fabric of spacetime itself. A pattern so faint it's invisible to the classical eye, but detectable in principle through its quantum gravitational effects. This quantum hair could solve one of the most vexing problems in modern physics, the black hole information paradox. If a black hole can be described by only mass, charge, and spin, then it has no way to remember what it consumed. The information about whether it ate a proton, a neutron, or an entire library is fundamentally lost. But if a black hole has quantum hair, these subtle imprints in its gravitational field could act as a form of external memory. The specific arrangement of the quantum fields around the horizon could be uniquely tied to the specific type of matter that fell inside. When an object crosses the event horizon, it wouldn't just vanish without a trace. It would leave a delicate quantum fingerprint on the black hole's exterior. This fingerprint wouldn't violate the classical no-hair theorem because it doesn't change the black hole's mass, charge, or spin in a measurable way. Instead, it exists as a quantum-level signature, a hidden layer of complexity that makes every black hole truly unique. The implications of this are revolutionary. It would mean that two black holes with identical mass, identical charge, and identical spin would not be perfect twins. Their quantum hairdos would be different, reflecting their distinct histories. This provides a potential mechanism for information to be preserved without being trapped inside the singularity. The information isn't lost, it's encoded in the hairstyle. Furthermore, as the black hole evaporates via Hawking radiation, this quantum hair could influence the radiation that escapes. The emitted particles wouldn't be completely random. They would carry tiny, encrypted traces of the information stored in the gravitational field, providing a pathway for the black hole to slowly and faithfully return all that it had seemingly destroyed. The discovery of quantum hair would fundamentally change our view of black holes from being the ultimate simplifiers of the cosmos to being complex objects with rich, hidden histories, seamlessly bridging the worlds of gravity and quantum mechanics and preserving the logical consistency of the universe. Now, let's tackle one of the most persistent and dramatic images from science fiction, the idea that falling into a black hole means being instantly shredded into a stream of atoms. While this fate is very real for smaller black holes, it turns out that if you choose your destination carefully, you could, in theory, survive the crossing of the event horizon itself. The key factor isn't magic technology, but the immense size of a supermassive black hole, like the one at the center of our own galaxy, Sagittarius A star. The force that would tear you apart is not the black hole's gravity as a whole, but the difference in gravity across your body, a phenomenon known as tidal force. Think of the ocean's tides on Earth caused by the moon's gravity pulling more strongly on the side of the planet facing it. Now, imagine that same principle applied on a personal and terrifying scale. With a typical stellar mass black hole, perhaps 10 times the mass of our Sun, the gravitational gradient is incredibly steep. Your feet, if you fell in feet first, would be pulled with significantly more force than your head. This difference would stretch you lengthwise while simultaneously compressing you from the sides, transforming you into a long, thin stream of particles in a process aptly named spaghettification. This would happen well before you even reach the event horizon, but scale changes everything. A supermassive black hole containing millions or even billions of times the mass of our Sun has an event horizon that is colossal. For Sagittarius A star, that boundary is over 12 million kilometers in radius. Because this immense mass is spread over such a vast volume, the gravitational pull at the event horizon is actually much weaker, and the gradient, the change in gravity from your head to your toes, is far more gentle. The point where tidal forces become lethal, known as the Roche limit, lies deep inside the event horizon for these giants. So, in a purely theoretical sense, you could cross the point of no return without immediately feeling a destructive pull. From your own perspective, as you fell feet first toward the horizon, you might not feel anything out of the ordinary at that precise moment. There would be no flashing alarm, no sudden barrier. You would simply float past an invisible boundary in space, a threshold you could only have calculated from the outside. Once across, your view of the universe would begin a profound and irreversible transformation. Looking outward toward the opening of the black hole's gravitational well, you would witness the entire future history of the cosmos play out in an incredible fast-forward. Due to the extreme time dilation predicted by general relativity, time for you would pass vastly slower than for the universe outside. You would see the light from stars and galaxies blue shifted into a blinding, concentrated ring of intense radiation above you, often called the photon sphere. You might watch as stars aged and died in seconds, galaxies collided and merged in a flash, and the cosmic background radiation shifted into a lethal bath of high-energy particles. The universe would appear to be accelerating toward its own heat death right before your eyes, all while you continued your inevitable journey toward the central singularity, which still awaits you somewhere in the future. This creates one of the most fascinating paradoxes in all of physics, a complete divergence of experience between you, the falling observer, and a friend watching you from a safe distance. From their perspective, the story is entirely different. As you approach the event horizon, the light you emit or reflect would take longer and longer to climb out of the gravitational well to reach their eyes. You would appear to slow down, moving in ever-slowing increments. The light would also redshift, becoming dimmer and dimmer, shifting from visible light to infrared, then to radio waves until you effectively faded from view. You would never, from their point of view, actually cross the event horizon. Instead, your image would seem to freeze there forever, a ghostly photograph plastered against the darkness, a permanent testament to your final moment. So, who is right? The answer, bizarrely, is that both perspectives are valid within their own reference frames. There is no single universal now in Einstein's universe. Your reality of a smooth crossing and their reality of your frozen image are both true descriptions of events from different points of view. This stark contrast highlights the profound way in which gravity and motion warp not just space, but the very flow of time itself, showing us that the universe is far stranger than our everyday intuition would ever allow. This notion that information might be preserved on a two-dimensional surface brings us to one of the most staggering theories in all of modern physics. A concept that suggests the very reality we experience in all its rich, three-dimensional splendor might be an elaborate illusion. This is the holographic principle, and its origins are deeply rooted in the thermodynamics of black holes, forcing us to reconsider the fundamental nature of information and dimensionality in the cosmos. The story begins with a surprising discovery about black holes in the 1970s. Physicist Jacob Bekenstein realized that a black hole's event horizon has entropy. Entropy is a measure of disorder, but in its most profound sense, it is a measure of the number of possible microscopic states a system can have, which is directly linked to the amount of information it contains. A burning log has high entropy because the ashes and smoke can be arranged in countless ways. The information about the original log is scrambled, but it still exists. Bekenstein proposed that a black hole's entropy is proportional to the surface area of its event horizon, not to the volume of space inside it. This was a radical departure. For every other object in the universe, entropy is a volume-based property. The fact that a black hole's information content seemed to be tied to its two-dimensional boundary was the first major clue that we might be thinking about reality in the wrong way. This idea was solidified by the work of physicists Gerard T. Hooft and Leonard Susskind, who took Bekenstein's insight and ran with it, formulating the holographic principle in its full glory. They proposed that this wasn't just a quirky property of black holes, but a fundamental law of the universe. The principle states that all the information needed to perfectly describe a volume of space can be encoded on its lower dimensional boundary. To understand this, think of an ordinary hologram on your credit card. It's a flat, two-dimensional piece of film, but when you shine light through it, it projects a stunningly realistic three-dimensional image. The holographic principle suggests our universe operates in a similar, albeit vastly more complex, way. The three-dimensional space we live in, with all its galaxies, stars, planets, and people, could be a projection from a vast, two-dimensional surface that surrounds us at the edge of the observable universe. In this view, the cosmos is like a cosmic movie screen, and we are the shadows dancing upon it, believing ourselves to be solid and three-dimensional when, at the most fundamental level, we are data points on an immeasurably vast flat surface. So, how does this connect back to black holes? They are the ultimate test case. When anything falls into a black hole, the holographic principle states that it doesn't vanish into a three-dimensional interior. Instead, the information about that object is smeared out and stored as flickering bits of data on the event horizon, the black hole's two-dimensional surface. Each tiny pixel on this surface is thought to be about a Planck length in size, the smallest possible unit of distance, and can hold a single bit of information. The total information capacity of the black hole is then simply the total number of these Planck-sized pixels that can fit on its horizon. As matter falls in, the event horizon expands, adding more pixels to its surface area, thus increasing its information storage capacity. The three-dimensional interior, with its mysterious depths and potential singularities, is not the primary reality. It is a holographic projection of the information stored on the bustling, two-dimensional surface of the horizon. The black hole is, in essence, the universe's most efficient hard drive. Now, take this logic and scale it up to its most breathtaking conclusion. If a black hole's interior is a holographic projection from its event horizon, could our entire universe be the same? This is the core of the theory that our cosmos is a hologram. In this model, the screen is not the edge of a black hole, but the boundary of the observable universe itself. The cosmic microwave background radiation, the remnant glow from the Big Bang, which forms a spherical shell around us at a distance of over 46 billion light-years. The fluctuations and patterns imprinted in this ancient light could, in theory, contain the encoded data for everything within the volume it encloses. Every galaxy, every human being, every thought you've ever had would be a complex decoding of the information stored on that distant, two-dimensional surface. We are not living inside a black hole in the traditional sense, but the physics that governs our universe may be isomorphic to the physics of a two-dimensional quantum field theory on its boundary. It's an idea that elegantly bridges the greatest divide in physics, the chasm between Einstein's general relativity, which describes the large-scale structure of spacetime, and quantum mechanics, which describes the small-scale behavior of particles. In the holographic universe, gravity and the three-dimensional world emerge from a quantum system that has no gravity at all, operating on a flat, lower-dimensional surface. The implications of this are enough to make your head spin. It suggests that the solidity of the world around us, the very feeling of depth and space, is a magnificent illusion, much like the three-dimensional image on a security hologram. Your sense of touching a table or seeing the moon in the sky is the result of an unimaginably complex calculation happening at the edge of everything. This doesn't mean our reality is fake or less real. The laws of physics still apply perfectly consistently within our projected world, but it does mean that the universe is far stranger and more interconnected than we ever imagined. It also provides a potential, powerful resolution to the black hole information paradox. If information is never truly inside a black hole's volume but is always stored on its surface, then there is no paradox about it being lost. When the black hole evaporates via Hawking radiation, that radiation is simply the slow, meticulous reading of the data off the horizon's surface, preserving the information perfectly. The holographic principle transforms black holes from information-destroying monsters into the ultimate teachers, showing us that the key to understanding the cosmos may not be to look deeper into the third dimension, but to learn to read the cosmic code written on the walls of our reality. Yet, this elegant idea of a holographic projection leads us directly to one of the most contentious and fiery debates in modern theoretical physics. A hypothesis that proposes the event horizon is anything but a smooth, uneventful place to cross. This is the black hole firewall paradox, a theory born from the desperate struggle to resolve the information paradox, and it suggests a far more violent fate for anything daring to approach a black hole's point of no return. The story of the firewall begins with a straightforward, logical argument. We know that Hawking radiation must carry information out to preserve quantum unitarity. For this to happen, the radiation emitted just outside the horizon must be intricately entangled with the radiation that was emitted earlier. However, for the infalling observer to have a smooth experience crossing the horizon, a cornerstone of general relativity, known as the equivalence principle, the radiation just outside the horizon must also be entangled with the particles that fell into the black hole long ago. This creates an impossible quantum triangle. A principle called monogamy of entanglement states that a quantum particle cannot be fully entangled with two different systems at the same time. It's the ultimate quantum loyalty test. A particle can be deeply entangled with one partner, but not with two. The firewall proposal makes a brutal choice to solve this loyalty conflict. It argues that to ensure the Hawking radiation escaping to the outside universe carries a pure, untangled stream of information, the connection between the outside radiation and its infalling partner must be severed. This sudden, violent breaking of the entanglement bond would release an astronomical amount of energy, transforming the event horizon from an invisible boundary into a literal wall of blazing, high-energy particles. An astronaut crossing this threshold wouldn't experience the serene free fall predicted by Einstein. They would be instantly vaporized, incinerated by a curtain of fire the moment they reached the event horizon. In this view, the black hole isn't a graceful spacetime curve but a cosmic kill zone, protecting its secrets with a shield of unimaginable fury. Unsurprisingly, this idea has sparked a firestorm of its own within the physics community, as it directly assaults a fundamental tenet of general relativity, the equivalence principle. This principle assures us that a freely falling observer in a gravitational field should feel no local effects. If you're in an elevator in free fall, you experience weightlessness, unable to tell whether you're in deep space or plummeting toward a massive object. Applying this to a black hole, it means you should cross the event horizon without noticing anything special. No jolt, no heat, no dramatic fanfare. The firewall shatters this elegant principle. It insists that the event horizon is a physically special place, a region of intense energy that would be glaringly obvious to any observer. This creates a stark either-or dilemma that cuts to the core of our understanding of physics. Either quantum mechanics is correct and information is preserved, but at the terrible cost of a firewall that violates general relativity, or general relativity holds and the horizon is smooth, but then quantum mechanics must be wrong and information is lost forever. It's a battle for the soul of physics, forcing a choice between two of our most successful and cherished theories. The debate has driven physicists to explore ever more exotic solutions to escape this grim either-or scenario. Some researchers propose that the firewall doesn't form immediately but develops later in the black hole's life, long after it has formed as a consequence of its advanced evaporation. Others suggest that the very concept of a sharp, locatable event horizon is the problem, and that quantum effects create a fuzzball or a blurry, dynamic boundary that avoids the paradoxical entanglement conflict altogether. There are even ideas that the intense computation required to decode the information from the Hawking radiation effectively prevents the firewall from forming for any realistic observer. The firewall hypothesis, for all its violence, has been an incredibly productive catalyst. It has forced a deeper and more nuanced conversation about what really happens when quantum fields meet intense gravity, highlighting that our classical intuitions are almost certainly inadequate for the task. It has pushed the entire field to scrutinize its most basic assumptions, proving that even an idea as shocking as a ring of fire can illuminate the path toward a truer, more complete theory of quantum gravity. But if the holographic principle and firewall paradox stretch our conception of reality, then the next theory threatens to shatter the very foundation of predictive science. We've been talking about black holes with the comforting assumption that their most dangerous features are safely locked away behind an event horizon, a cosmic shield that protects the rest of the universe from the infinite chaos of a singularity. This isn't just a convenient idea, it's formalized in a concept known as the cosmic censorship hypothesis, proposed by the renowned physicist Roger Penrose. In essence, this hypothesis is a bet on the good manners of the universe. It suggests that nature abhors a naked singularity, and any time a singularity forms through gravitational collapse, the laws of physics will always, without fail, clothe it in an event horizon, hiding its infinite violence from our view. This cosmic curtain ensures that the unpredictable insanity at a singularity's core cannot affect the outside universe, preserving our ability to use physics to predict the future. Now imagine that curtain being torn away. This is the terrifying and thrilling possibility of a naked singularity, a point of infinite density that is completely exposed to the rest of the cosmos, with no event horizon to shield us from its wrath. The mathematics of general relativity does not explicitly forbid such an object. In fact, the equations suggest that under very specific and extreme conditions, a singularity could form without this protective barrier. One of the most likely scenarios involves the collapse of a star that is spinning at a significant fraction of the speed of light. As such a star collapses, its rotation would intensify, much like a spinning ice skater pulling in their arms. This rapid spin could potentially distort the forming singularity and the spacetime around it so dramatically that an event horizon fails to form completely, leaving the raw, uncloaked singularity open for the universe to see. The consequences of such an object existing would be nothing short of revolutionary, and not necessarily in a good way. The primary casualty would be predictability, the very bedrock of science. Within the event horizon of a normal black hole, the laws of physics as we know them break down. Causality, the rule that cause must precede effect, can be violated. But this is fine in a cosmic sense because that violation is hidden. The insanity is quarantined. A naked singularity would unleash that lawlessness upon the entire universe. At its surface, the concept of before and after could become meaningless. The deterministic flow of time that we rely on to understand everything from planetary orbits to chemical reactions would simply cease to function in its vicinity. You could, in theory, have effects that precede their causes, creating paradoxes that make time travel look simple. It would be a place where the universe's rulebook is not just rewritten but actively set on fire. This leads to one of the most mind-bending implications: the potential for naked singularities to function as natural time machines. The infinitely warped spacetime around such an object could create what are known as closed time-like curves. These are paths through spacetime that loop back on themselves, allowing an object to travel into its own past. While some theoretical wormhole solutions also allow for this, a naked singularity could achieve it without the need for exotic matter to stabilize a tunnel. Simply by flying a spaceship on a precise trajectory around the naked singularity, you could end up arriving at a point in spacetime before you even left. This isn't the controlled time travel of science fiction. It's a fundamental breakdown of temporal order, opening the door to all the classic paradoxes, like going back in time and preventing your own birth. The very fact that such a thing is mathematically possible within general relativity is a stark warning that our understanding of gravity is incomplete. So why, if the math allows it, does the universe seem to lack any confirmed examples of these objects? Most physicists hold a deep-seated belief, backed by considerable work, that nature actively prevents their formation. This is the essence of the cosmic censorship hypothesis. It's a conjecture that the universe has a built-in safety mechanism. Perhaps during the chaotic collapse of a rapidly spinning star, processes we don't yet fully understand, like the emission of gravitational waves or quantum effects, always shed just enough angular momentum to allow an event horizon to form at the last possible second. It's as if the universe, faced with the prospect of exposing its most shameful secret, always finds a way to pull the sheets up at the last moment. The search for a naked singularity is therefore one of the great quests in theoretical physics. Finding one would be a monumental discovery, forcing a complete rewrite of our understanding of gravity, causality, and the very nature of time. But until one is found, the prevailing wisdom is that cosmic censorship is a law of nature, not just a helpful suggestion, protecting the logical consistency of our reality from the infinite weirdness waiting at the edge of existence. But perhaps the most dizzying possibility of all is that these cosmic engines of gravity could be used to construct the ultimate machine, a time machine. This isn't about traveling to the future, which is relatively straightforward thanks to time dilation. If you orbit a black hole closely and return, you will have experienced less time than everyone else. Traveling into the past, however, is a different matter entirely, and it's a possibility that emerges from the most complex type of black hole we know, the rotating Kerr black hole. Unlike its simpler, non-spinning cousin, a Kerr black hole doesn't just have a point-like singularity. Its rapid rotation flings the singularity into a ring shape. This ring singularity is not hidden deep within an impenetrable barrier. It's surrounded by a series of nested horizons and a region called the ergosphere, an oblate region of warped spacetime where dragging everything along with it is impossible to remain stationary. It's within this intricate gravitational labyrinth that the paths to the past might theoretically be found. The hypothetical journey to yesterday would be a terrifyingly precise maneuver. First, your spacecraft would need to navigate the ergosphere, a region where spacetime itself is being twisted by the black hole's spin like a cosmic whirlpool. Here, you could extract energy from the black hole's rotation, but the real goal is to penetrate deeper, past the outer event horizon and toward the inner or Cauchy horizon. This inner horizon is a boundary of mathematical prophecy, a place where the equations of general relativity suggest that the predictable nature of spacetime breaks down. It's here, in the turbulent space between the inner and outer horizons, that the extreme frame dragging could warp the fabric of the cosmos so severely that timelines bend back on themselves, forming what physicists call closed time-like curves. These are not tunnels through space, but paths through spacetime that loop back to an earlier point in time. By executing a complex slingshot maneuver around the ring singularity within this zone, without actually hitting it and being annihilated, you could, in theory, find yourself on a trajectory that returns you to the universe before you even began your journey. The immediate and profound problem with this is the explosion of paradoxes it creates, the most famous being the grandfather paradox. What happens if you travel back in time and prevent your own grandfather from meeting your grandmother? Your own birth would then become impossible, meaning you could never have traveled back in time to commit the act in the first place. This creates a logical inconsistency that the universe seems to abhor. Physics offers a few potential solutions, but none are comfortable. One is the idea of a single, self-consistent timeline where your actions in the past were always a part of history. You might discover that your attempt to change events was in fact the very cause of those events unfolding as they did. Another, more radical idea from quantum mechanics is the many worlds interpretation, where your time-traveling act creates a branch in reality, a new, parallel universe where history changes, leaving the original timeline intact. But these are philosophical band-aids on a gaping wound in our understanding of causality. When we move from the beautiful mathematics to the harsh light of physical plausibility, the entire concept of a black hole time machine collapses under its own weight. The region where closed time-like curves are predicted to exist is violently unstable. Even the tiniest perturbation, like a single particle of dust or the energy carried by your own spacecraft, would likely trigger a feedback loop of infinite energy density, obliterating the time loop in a cataclysm of physics. Furthermore, actually reaching this inner sanctum is almost certainly a one-way trip to destruction. The inner horizon may not be a place of calm passage, but a mass inflation singularity, a wall of infinitely blue shifted radiation from the entire future history of the universe focused into that one point. Crossing it would be like flying into the heart of a Big Bang. So, while the Kerr metric provides a tantalizing mathematical playground that suggests time travel is not forbidden by general relativity, the universe appears to have installed every conceivable failsafe, from logical paradoxes to lethal physical barriers, to ensure that the past remains forever a foreign country we can only visit in our memories. This brings us to a theory that suggests the most exotic objects in the cosmos might not be distant monsters, but could be buzzing right here in our own cosmic backyard, perhaps even passing through the room you're in right now. We've explored supermassive giants and stellar mass remnants, but what about the smallest conceivable black holes? The concept of mini black holes or primordial black holes proposes that black holes aren't only born from dying stars. Instead, a vast, unseen population of them could have been forged in the incredible pressures of the Big Bang's first moments. In that seething, dense cauldron of the early universe, random quantum fluctuations could have been amplified to such an extreme that tiny pockets of space collapsed directly into black holes. Unlike their stellar cousins, these primordial black holes could have formed with virtually any mass, from a planet's worth of material compressed into a sphere the size of a marble, to a mountain's mass squeezed into the width of a single atom. This means a black hole doesn't have to be a colossal engine of destruction. It could be a microscopic, hyper-dense grain of sand, a cosmic ghost drifting silently between the stars. The most fascinating possibility is that these tiny titans could be far more common than the giant black holes we can easily observe. If the theory is correct, our Milky Way galaxy could be filled with a vast, dark swarm of them, a halo of invisible specks whose collective gravity could even contribute to the mysterious dark matter that holds galaxies together. And if that's the case, then our solar system and even our planet would be constantly bombarded by these subatomic or asteroid-sized projectiles. A black hole with the mass of an asteroid would be smaller than a proton, and one with the mass of Earth would be roughly the size of a peanut. Their tiny size means their event horizons are minuscule, and their gravitational pull only becomes significant at an extremely short range. So, if one were to pass through the Earth, it wouldn't suck the planet into a vortex. Its journey would be more like that of a bullet, but with some very strange and detectable side effects. So, how would we ever know if a microscopic black hole zipped through our planet? The key signature wouldn't be a giant gravitational pull, but a unique and sudden release of energy. As this incredibly dense object moves through a medium like the Earth's crust or its iron core, the atoms in its path are subjected to unimaginable tidal forces. The black hole's intense gravity would violently pull on the nuclei of these atoms, causing them to vibrate and heat up rapidly. This process, known as accretion, would generate a flash of radiation, primarily in the form of X-rays or gamma rays. Furthermore, the sheer friction of its passage would deposit a linear trail of heat, leaving a thin, needle-like track of superheated rock or magma in its wake. For a sufficiently massive mini-black hole, this could even generate a detectable seismic signal, a sharp, distinct rumble propagating through the planet, unlike any conventional earthquake because it would originate from a single moving point deep underground. Scientists have not left this incredible possibility to pure speculation. They have set up sophisticated experiments to hunt for these elusive objects. One of the most promising methods involves using the planet itself as a giant detector. Researchers have proposed using dense networks of highly sensitive seismometers, the same instruments that measure earthquakes, to listen for the unique acoustic fingerprint of a passing primordial black hole. They would be searching for a specific pattern, a seismic wave that starts deep within the Earth and moves in a straight line at incredible speed, accompanied by a corresponding flash of electromagnetic radiation that could be picked up by satellites monitoring for gamma-ray bursts. Other experiments look for the telltale flashes of light when a mini black hole passes through a large volume of a transparent medium. Like the sensors in giant neutrino observatories or even the human eye itself, there are hypothetical, though highly improbable, accounts of a mini black hole passing through someone's retina and causing a spontaneous, unexplained flash of light. The hunt also extends to space. Telescopes scan the skies for the telltale flicker of a primordial black hole passing in front of a distant star. Because of its gravity, the black hole would act as a lens, bending the starlight and causing the star to temporarily brighten, a phenomenon known as gravitational microlensing. Surveys looking for dark matter have used this technique for years, and while they have ruled out primordial black holes making up the entirety of dark matter, a significant population of asteroid mass or planet mass black holes is still a very real possibility. Discovering just one of these objects would be a monumental breakthrough. It would provide a direct window into the conditions of the very early universe, confirming a bold prediction about the Big Bang. It would also offer a compelling, non-particle candidate for dark matter, suggesting that the invisible stuff holding galaxies together isn't an unknown particle, but countless fragments of the universe's explosive birth, each a silent, miniature universe of its own, forever wandering the cosmic dark. We've followed the epic journey of a black hole from its violent birth to its slow evaporation through Hawking radiation, but what happens in the very last moment? When the final bit of mass energy is radiated away, does the black hole simply vanish with a silent pop, or does it leave something behind? The answer may lie in one of the most speculative, yet profoundly beautiful, theories in all of physics. The idea that a dying black hole could be reborn as a white fountain. After trillions upon trillions of years of leaking away its mass, a black hole enters its final, frantic seconds. The evaporation process, once imperceptibly slow, becomes a runaway explosion. The black hole's temperature soars to billions of degrees, and it emits a final, intense flash of particles and radiation. According to the standard Hawking calculation, this is the end. The black hole vanishes, and with it, according to the old view, all the information it ever consumed. But many physicists find this absolute disappearance unsatisfying. It's like a cosmic story that just stops mid-sentence. The quest for a more complete ending has led to two compelling and very different visions of the ultimate fate. One possibility is that the black hole leaves behind a relic, a stable, indestructible particle holding the very last bit of the black hole's original mass. This isn't just any particle. Its mass would be anchored at the Planck scale, the smallest possible unit of mass in the universe, a value determined by the fundamental constants of nature. This Planck mass remnant would be unimaginably tiny, yet incredibly dense, a fossil of a once great cosmic giant. It would be stable because it can't evaporate any further. Hawking radiation would effectively cease at this scale. The existence of such relics would solve the information paradox in a radical way. All the quantum information that ever fell into the black hole wouldn't be carried away by the radiation. It would be frozen, locked forever inside this ultimate time capsule. The universe would slowly become littered with these invisible, ancient artifacts, each one a silent tombstone for a long-dead black hole. However, this idea creates its own cosmic headache. An infinite number of these remnants, each with potentially different internal states storing different information, would imply the universe has an infinite number of possible microstates. This clashes with our understanding of cosmology and the finite entropy of the observable universe, making this a controversial, though fascinating, final chapter. The other, more dramatic, theory proposes that the black hole's death is not an end but a transformation. In its final moment, the remnant doesn't just sit there, it undergoes a quantum bounce. The intense gravitational collapse that created the black hole eons ago finally reverses. This isn't a collapse into a singularity, but a rebound from a Planck-scale object. What emerges from this bounce is not a black hole, but its theoretical opposite, a white hole. But this wouldn't be the permanent, universe-violating white hole of classical relativity. It would be a transient, explosive event, a white fountain. Imagine the black hole's life as a film played in reverse. After an eternity of sucking things in, the process suddenly flips. The white fountain would be a brief, brilliant outburst, a geyser of energy and information spraying back out into the universe. It would be the black hole's final act of cosmic restitution, returning every last bit of the mass and information it had locked away, effectively resolving the information paradox by giving back what was borrowed. The energy release in this final event would be spectacular. All the remaining mass energy of the black hole, now concentrated at the Planck scale, would be converted into a flash of high-energy particles and radiation. For a stellar mass black hole, this final burst would be more energetic than a supernova, a fittingly grand finale for an object that once dominated its corner of spacetime. This white fountain phase would be incredibly short-lived, likely lasting only a fraction of a second before the energy is fully expended and the object winks out of existence for good. The challenge, of course, is that we live in a universe far too young for any black hole born from a star to have reached this final stage. The only chance of observing such an event would be if tiny, primordial black holes from the Big Bang were now reaching the end of their lives. Astronomers have searched for the unique gamma-ray signature of such explosions, but so far without any confirmed detections. Whether a silent relic or a brilliant fountain, the ultimate fate of a black hole forces us to confront the deepest questions about information, time, and whether anything in the cosmos truly ever ends, or if it merely changes form in the endless cycle of transformation. Moving from the microscopic to the cosmic, we arrive at a theory that reimagines the very concept of a home world. We are accustomed to planets orbiting stars, basking in their warm, life-giving light. But what if a star is not the only gravitational anchor for a planetary system? The idea that black holes could have their own planets sounds like the premise of a science fiction epic, yet it is a scenario that emerges naturally from our understanding of how planetary systems form. The key ingredient isn't the type of central object, but the presence of a substantial debris disk. We see this process unfold around young stars, where clouds of gas and dust in a protoplanetary disk gradually clump together, eventually forming planets, asteroids, and comets. There is no fundamental law of physics that says this process must be exclusive to stars. If a black hole, whether a stellar mass remnant or a supermassive giant, is surrounded by a sufficiently massive and stable disk of material, the same gravitational and collisional processes could, over millions of years, give rise to a family of planets. The source of this material could be just as dramatic as the black hole itself. For a stellar mass black hole, the disk might be formed from the mangled remains of a companion star it is slowly consuming, or from the shattered fragments of planets that survived the original star's death throes. Around a supermassive black hole, like the one at the center of our galaxy, the potential reservoir of material is vaster still. The galactic core is a crowded, chaotic place filled with stars, gas clouds, and dust. Collisions between passing stars or the tidal disruption of a gas cloud could easily create a vast, swirling torus of debris, a fertile ground for planet formation on a truly monumental scale. These wouldn't be your typical, cozy planets nestled close to a sun. They would be dark, nomadic worlds born from chaos and bound by gravity to the most powerful object in their vicinity. The environment on such a world would be unlike anything we can truly comprehend. Forget the rhythm of day and night as we know it. A planet orbiting a solitary black hole would be a place of perpetual twilight, a landscape illuminated by two primary and utterly alien light sources. The first would be the accretion disk itself if it is actively feeding. This swirling maelstrom of superheated gas and dust would glow with an intense, hellish radiance, casting shifting, lurid colors across the planet's surface. It would not provide the steady, full-spectrum light of a star, but a fierce, localized glare, creating stark shadows and a day side perpetually bathed in the light of a cosmic furnace. The second source of illumination would be the cold, uniform glow of the cosmic microwave background radiation, the remnant heat from the Big Bang. This would provide a faint, omnipresent light, a ghostly backdrop against which the more violent light of the disk would play. For any form of life to arise and persist in such an environment, it would have to be radically different from anything on Earth. The primary energy source would not be photosynthesis, but chemosynthesis or perhaps even radiation-driven processes, drawing energy from the intense X-rays and gamma rays pouring from the accretion disk or from the planet's own internal geothermal heat, generated by the immense tidal forces of the black hole's gravity. The planet would need to orbit at a very precise distance close enough to be warmed by the disk's energy, but far enough away to avoid being sterilized by its radiation or shredded by its tidal forces. A thick, protective atmosphere would be essential to shield the surface from lethal cosmic rays and to help distribute what little heat is available. Life, if it existed, might huddle around volcanic vents on a frozen world or thrive in deep subterranean oceans, completely independent of stellar light, its entire ecosystem powered by the dark, gravitational heart of the system. The search for these dark planetary systems is no longer pure speculation. It is becoming a realistic goal for our most powerful observatories. While detecting a planet directly by the dim reflection of an accretion disk's light is incredibly challenging, astronomers have other methods. The same gravitational microlensing techniques used to hunt for rogue planets or primordial black holes could also reveal planets bound to black holes. If a black hole with a planetary system passes in front of a distant star, the gravity of both the black hole and its planets would warp the starlight, creating a complex, telltale signature in the resulting light curve. Next-generation telescopes, like the Nancy Grace Roman Space Telescope or the Extremely Large Telescope, will have the sensitivity and monitoring capabilities to detect these subtle signals. Furthermore, the Atacama Large Millimeter Array and future instruments could directly image the dusty debris disks around nearby supermassive black holes, looking for the gaps and patterns that suggest protoplanets are coalescing within them. Finding just one such world would forever change our perspective on the diversity of planetary systems, proving that planets can form in the most extreme and hostile environments imaginable, orbiting the ultimate symbol of cosmic power and mystery. Consider the ultimate act of creation, not from a divine hand, but from an act of cosmic destruction. We've explored the idea that our universe might have been born from a black hole, but this theory takes that concept to its logical and breathtaking extreme, that the Big Bang itself was not a unique, singular event, but simply the formation of a black hole in a vast, pre-existing cosmos. Imagine a universe much like our own, but perhaps with different physical laws or even more dimensions of space. In that parent universe, a star of unimaginable scale reaches the end of its life. Its core collapses and the gravitational forces are so overwhelming that they don't just form a black hole as we understand it. Instead, the collapse punches through the very fabric of its native spacetime. The matter and energy, compressed to a state of near-infinite density, don't just stop at a singularity. According to this model, they reach a point where the repulsive force of quantum gravity becomes dominant, causing a monumental rebound, a bounce. This bounce, from our perspective inside the new realm, is the Big Bang. The initial incomprehensible heat and density of our universe's first moment was simply the fiery birth cry of our cosmos, emerging from the collapsed core of a star in another reality entirely. This vision elegantly integrates with a class of models known as cyclic cosmologies, which propose that the universe undergoes endless cycles of expansion, contraction, and rebirth. In the traditional Big Bang model, the universe has a definite beginning, which creates philosophical and scientific puzzles about what came before. But if the Big Bang was a black hole bounce, there is no before in the linear sense we think of. There is only the ongoing, cyclical process of one universe giving birth to another. Our universe expands, cools, and forms galaxies, stars, and planets. Eventually, over trillions of years, it may stop expanding and begin to contract, or perhaps its expansion will continue forever. But in regions where black holes form, new universes are constantly being spawned. Each black hole is a portal, a nexus where the fabric of one spacetime pinches off and gives rise to an entirely new, self-contained continuum. Our entire observable universe, with its hundreds of billions of galaxies, could be the interior of one such black hole existing in a much larger meta-universe. This leads to the staggering concept of an eternal, self-reproducing multiverse, a cosmic ecosystem driven by a form of natural selection. Physicist Lee Smolin's theory of cosmological natural selection proposes that each baby universe inherits its fundamental physical constants like the strength of gravity or the mass of an electron, from its parent, but with slight random variations, much like genetic mutations in biology. Universes that have physical laws conducive to forming many stars and consequently many black holes will produce more offspring universes. Over an eternity of cycles, the multiverse becomes dominated by universes that are exceptionally efficient at making black holes. This provides a powerful, non-theological explanation for one of the greatest mysteries in science: why our universe seems so exquisitely fine-tuned for complexity. The constants of nature appear perfectly calibrated to allow for the existence of stars, planets, and life. If we live in a universe that is a prolific black hole producer, then those same finely tuned constants, the ones that allow massive stars to form and then collapse, are also the very same constants that inadvertently allow for the formation of carbon, oxygen, and the complex chemistry necessary for life. We aren't the purpose of the universe. We are a fortunate byproduct of a cosmos that is exceptionally good at replicating itself. The implications of this are as humbling as they are magnificent. It suggests that the vast cosmos we see is not the entirety of existence, but merely one branch on an infinite, ever-growing tree of realities. Every black hole we observe, from the tiny, hypothetical primordial ones to the supermassive giants at the centers of galaxies, is not a dead end, but a potential womb for a new cosmos. The terrifying darkness of a black hole's event horizon is not a wall, but a horizon in the truest sense, the point beyond which a new world begins. This theory transforms our understanding of our place in the grand scheme, suggesting that the cycle of birth, life, and death is not just a biological imperative, but a cosmic one, playing out on the grandest possible stage across an eternity of time and an infinity of spaces. Up until now, we've primarily thought of a black hole's power in terms of its immense gravity, defined by its mass and spin. But there's a third, often overlooked property that could unleash a completely different kind of cosmic fury: electric charge. While most black holes in nature are thought to be nearly neutral, having shed any significant charge quickly after their formation, the theoretical possibility of a highly charged black hole opens up a realm of phenomena that makes even a supernova look tame. This is the realm of the Kerr-Newman black hole, the most complete solution to Einstein's equations, describing a black hole that is not only rotating but also carries a substantial electric charge. When you combine the intense gravity and frame dragging of a Kerr black hole with a powerful electric charge, you create an engine for some of the most powerful and focused energy releases in the universe. The true magic happens when this charged, spinning black hole is immersed in a sea of plasma, such as the accretion disk of superheated gas and dust that often surrounds these objects. The black hole's rotation, combined with its immense gravity, drags the very fabric of spacetime around with it, a phenomenon known as frame dragging. This spinning spacetime, in turn, whips the surrounding magnetic fields, which are anchored in the ionized plasma of the accretion disk, into an incredibly tight and powerful coil. The result is a magnetic field of almost incomprehensible strength, trillions of times more powerful than any magnet we could ever create on Earth. This isn't a passive field. It's a dynamic, twisted web of energy that acts like a colossal particle accelerator, channeling and focusing the chaotic energy of the infalling matter. Now introduce the black hole's electric charge into this volatile mix. In the environment around the black hole's poles, regions that are relatively clear of the turbulent accretion disk, the conditions become perfect for a cosmic short circuit. The intense magnetic fields generated by the spinning plasma can induce staggering electric potentials. We're talking about voltages so high they dwarf the total energy output of entire galaxies. This immense potential difference seeks the path of least resistance, and it finds it along the magnetic field lines that spear out from the black hole's rotational poles. When the electrical stress becomes too great, the vacuum of space itself breaks down. It erupts in a catastrophic discharge, a bolt of cosmic lightning of unimaginable scale. This isn't lightning as we see on Earth. It's a relativistic jet of electrons and positrons, matter and antimatter, accelerated to nearly the speed of light. We may have already witnessed the effects of this incredible process. The most powerful and persistent electromagnetic phenomena we observe in the universe are the relativistic jets that scream from the cores of active galactic nuclei, believed to be powered by supermassive black holes. These jets, which can stretch for millions of light years, punching out of their host galaxies, are beams of pure energy. They are so bright they can outshine every star in the galaxy combined. The leading theoretical model for how these jets are formed and collimated, or focused into such narrow beams, involves exactly this process: the extraction of rotational energy from a black hole via its immense coiled magnetic fields. In the case of a charged Kerr-Newman black hole, the electrical discharges would supercharge this mechanism, creating jets that are not just streams of plasma, but focused bolts of raw electrical power, capable of reionizing vast tracts of intergalactic space and influencing star formation in galaxies millions of light-years away. This cosmic lightning is more than just a spectacular light show. It is a fundamental force of construction and destruction, shaping the evolution of the largest structures in the cosmos. Now, let us turn our gaze inward from the vast expanse of the cosmos to the intricate universe contained within our own minds. We arrive at one of the most speculative and controversial theories on our list, a proposal that ventures to connect the physics of the largest, most destructive objects in existence with the very phenomenon of conscious experience itself. This is the fringe idea that the processing of information within the brain might share profound mathematical similarities with how information is processed at a black hole's event horizon. It is crucial to state from the outset that this is not mainstream science. It is a provocative, philosophical exploration that sits at the boundary of theoretical physics and neuroscience, an attempt to find a common language between the physics of the very large and the very complex. The foundation of this audacious connection rests upon the concept of information. In the world of quantum mechanics, information is fundamental. The state of every particle, the entanglement between them, the entire history of a system. This is all information. We've already seen how the holographic principle suggests that the information within a volume of space, like the interior of a black hole, can be encoded on its two-dimensional boundary, the event horizon. This is a specific mathematical relationship where a three-dimensional reality is projected from a two-dimensional surface teeming with information bits. Now shift your perspective to the human brain. The brain is in its own right an astonishing information processing system. Your thoughts, memories, and sensations are all represented by the states of billions of neurons and the trillions of synaptic connections between them. The patterns of electrical and chemical activity create the rich, three-dimensional tapestry of your conscious experience from the underlying, two-dimensional layers of the cerebral cortex, the deeply folded outer layer of the brain where higher-order processing occurs. Some theorists, like the renowned physicist Roger Penrose and anesthesiologist Stuart Hameroff, have proposed that consciousness arises from quantum processes deep within the neurons, specifically within structures called microtubules. While their specific model, known as orchestrated objective reduction, is highly debated, it opens the door to a more general question: could there be a formal analogy between the two systems? In a black hole, information from a three-dimensional volume is holographically stored and processed on a two-dimensional surface. In the brain, a three-dimensional conscious experience may emerge from information processing on the two-dimensional sheets of the cortical layers. In both cases, a lower dimensional boundary seems to be responsible for generating or encoding a higher dimensional reality. This isn't to say your brain contains a tiny black hole. Rather, It suggests that the fundamental mathematical principles governing information and its relationship to space and dimensionality might be universal, applying to complex systems regardless of their scale. This leads to the concept of the brain as a kind of internal cosmology. Just as a black hole has an event horizon that separates the knowable outside from the unknowable interior, our own consciousness could be seen as having a kind of perceptual horizon. Our senses gather information from the outside world, which is then processed and encoded within the neural networks of our brain. This internal model of reality is our personal universe, and the boundary between the raw, unprocessed sensory data and our coherent conscious experience could be thought of as a cognitive event horizon. Furthermore, the phenomenon of memory has a curious parallel. When information falls into a black hole, according to the holographic principle, it is not lost but scrambled and imprinted on the horizon. Our own memories are not perfect, high-fidelity recordings. They are reconstructed, often scrambled, and reinterpreted each time we recall them. The process of remembering is less like playing a video and more like piecing together a story from fragments, not unlike the theoretical process of reconstructing information from the Hawking radiation of an evaporating black hole. It is vital to approach this idea with a heavy dose of scientific humility. The differences between a black hole and a brain are, of course, colossal. A black hole is a vacuum solution to gravity, governed by general relativity and quantum field theory in curved spacetime. The brain is a wet, warm, and noisy biological system, and whether quantum coherence can be maintained in such an environment to play a role in consciousness is a major point of contention. Most neuroscientists believe classical physics is sufficient to explain neural processing. This theory, therefore, remains in the realm of a compelling metaphor, a mathematical analogy that is fascinating to contemplate but lacks any empirical evidence. It serves more as a philosophical tool, forcing us to consider consciousness not as a magical byproduct of biology, but as a physical process that might be subject to the same deep structural laws that govern the rest of the cosmos. It hints that the principles of information, entropy, and dimensionality might be the common thread weaving together the mind and the universe, suggesting that in our quest to understand the stars above and the self within, we may ultimately be exploring two different expressions of the same fundamental reality. We have journeyed through the lives of black holes from their microscopic beginnings to their potential roles as cosmic parents, but this leads to a profound question about their ultimate potential. Is there a ceiling, a final limit to how immense a black hole can become? We often picture these gravitational giants growing without bound, consuming everything in their path, but nature has a tendency to impose balance even on the most dominant forces. The evidence we see in the cosmos today certainly points toward a kind of practical limit. The supermassive black holes we observe, like the behemoth at the heart of galaxy M87, which is about 6.5 billion times the mass of our Sun, or the one in the galaxy home 15A, which is roughly 40 billion solar masses, are staggeringly large. Yet they are not infinitely so. They seem to plateau, suggesting that something is putting the brakes on their gluttonous expansion. The primary mechanism for this cosmic diet is believed to be the very process that fuels their growth, accretion. As vast amounts of gas and dust spiral inward, forming a superheated accretion disk, the conversion of gravitational energy into radiation is astoundingly efficient. This process doesn't just create light, it creates an immense outward pressure. When a black hole is feeding vigorously, the radiation pouring from its accretion disk can become so intense that it literally pushes back against the incoming stream of material. Imagine a bonfire so ferocious that its own heat prevents anyone from adding more wood. This is a phenomenon known as radiation pressure, and for the most massive black holes, it establishes a fundamental equilibrium called the Eddington limit. This is the point at which the outward radiation pressure perfectly balances the inward pull of gravity, effectively shutting off the main course of the black hole's meal and forcing it to grow at an exponentially slower rate, only nibbling on the occasional star or gas cloud that strays too close. But the environment itself can also starve a black hole of its future sustenance. In many mature galaxies, the central regions become red and dead, vast expanses where the interstellar gas has been either used up in star formation or blown away by powerful stellar winds and supernova explosions. A black hole in such a galactic retirement home simply has very little left to eat. Furthermore, the black hole's own past activity can be its undoing. During its active quasar phase, the incredible energy output from its jets and radiation can heat and expel the surrounding galactic gas reservoir, the very fuel it needs for future growth. It's a self-regulating cycle of feast and famine, where the black hole's most violent outbursts ensure its own long-term starvation. This intricate feedback loop between a black hole and its host galaxy is now seen as a cornerstone of galactic evolution, explaining why we don't see black holes that have consumed their entire galaxy. They effectively turn off their own food supply long before that can happen. However, this discussion of limits is based on the universe as we see it today, a snapshot in cosmic time. If we project our vision trillions of years into the future, into the era of the so-called degenerate era, a different and more terrifying possibility emerges. In this far future cosmos, stars will have long since burned out, and galaxies will have drifted apart due to the relentless expansion of the universe. In this dark, diffuse environment, the primary way a black hole could gain mass would shift from accreting gas to a slower, more sinister process: the gradual capture of the sparse, dark matter that permeates space, and more significantly, the direct collision and merger with other black holes. Over timescales that dwarf the current age of the universe, the supermassive black holes at the centers of galactic clusters could sink together through the emission of gravitational waves and merge, creating monsters of truly incomprehensible scale. This leads to a speculative but fascinating theoretical upper bound. Some cosmological models suggest that in the absolute farthest future, the very expansion of the universe could impose a final limit. If dark energy continues to accelerate the cosmos's expansion, eventually all other galaxies will be pushed beyond our cosmic horizon. The black holes within our own gravitationally bound cluster would merge into one final, ultimate black hole containing the mass of thousands of galaxies. But then nothing else would ever fall in. It would sit in isolated darkness, its growth permanently halted not by its own feedback but by the emptiness of the cosmos itself. It would be the last colossal structure, a dark monarch ruling over a kingdom of nothing, slowly evaporating over eons through Hawking radiation, its reign ending not with a bang but with the faintest, coldest whisper. Now, let's turn our attention from the solitary life of a black hole to a spectacular cosmic dance that ends in a cataclysmic merger, an event so powerful it can literally kick the resulting monster clear out of its galactic home. We've been exploring the gravitational wave universe through observatories like LIGO and Virgo for several years now, and with each new detection of colliding black holes, we learn something astonishing. The initial image might be one of a perfect, symmetrical union, but the reality is far more chaotic and violent. When two black holes spiral inward, locked in a final, fatal embrace, they ripple the fabric of spacetime itself, sending out gravitational waves that carry away immense amounts of energy and momentum. For the merger to be perfectly symmetrical, this emission would have to be the same in all directions, like a spherical explosion. But nature is rarely so tidy. The black holes are almost always spinning, and their orbits are tilted and precessing, creating a highly asymmetrical outburst of gravitational radiation. This lopsided emission has a profound consequence, acting like a rocket engine on the final, merged black hole. Imagine firing a gun, the bullet shoots forward, and the gun recoils backward into your shoulder. In a similar way as the final, intense burst of gravitational waves is ejected preferentially in one direction, the newborn black hole recoils in the opposite direction. This is the black hole kick, a gravitational slingshot of unimaginable power. The speeds involved are truly mind-boggling. Theoretical models and the data from gravitational wave events suggest that these kicks can propel the black hole at velocities exceeding 5,000 kilometers per second. To put that in perspective, that's more than 1% of the speed of light, fast enough to cross the entire United States in the blink of an eye. At such tremendous velocity, the black hole has far more than the escape velocity needed to break free from the gravitational pull of its host star cluster, its galaxy, or even its entire galactic group. It becomes a rogue, hypervelocity black hole, condemned to wander the immense dark voids between galaxies for eternity. The evidence for these cosmic cannonballs, while indirect, is compelling. Astronomers have observed a number of supermassive black holes that appear to be displaced from the exact centers of their galaxies, or even completely unmoored, racing through intergalactic space. One of the most famous candidates is an object known as CD42, a quasar where the brilliant source of light, the supermassive black hole's accretion disk, is located tens of thousands of light years away from the galactic core. The most plausible explanation is that this black hole received a tremendous kick from a previous merger, and we are witnessing it in the act of being ejected. Another line of evidence comes from the detection of gravitational wave events themselves. By carefully analyzing the waveform, the specific chirp signal that LIGO and Virgo detect, scientists can infer the properties of the final black hole, including any net velocity it might have inherited from the asymmetrical merger. While pinning down the exact kick speed from a single event is challenging, the statistical collection of mergers is beginning to paint a picture that confirms these powerful recoils are a common and dramatic feature of the black hole life cycle. The implications of this phenomenon for galactic evolution are deep and far-reaching. In the early universe, galaxies grew primarily through mergers and acquisitions, with smaller galaxies colliding to form larger ones. Each of these galactic collisions would have brought their central supermassive black holes together, eventually leading to a series of violent mergers in the new galactic core. If these mergers frequently produced powerful kicks, it could explain why some galaxies today appear to lack a central supermassive black hole altogether. It may have been unceremoniously evicted billions of years ago. This ejection process acts as a form of natural population control, regulating the growth of the very largest black holes and preventing them from becoming utterly gargantuan. Furthermore, a galaxy that loses its central black hole is a fundamentally different environment. The black hole's gravity helps to stabilize the central star cluster, and its energetic feedback during active phases helps to regulate star formation. A galaxy that has had its central engine ripped out might experience uncontrolled bursts of star formation or possess a strangely diffuse core, a permanent scar from a violent event in its deep past. The discovery of these gravitational kicks transforms our view of black hole mergers from a simple act of consolidation into a dynamic galaxy-shaping process, where the most massive objects in the universe can be sent careening into the cosmic dark, forever changing the galaxies they leave behind. But if black holes can be ejected from their galaxies and shape cosmic evolution through their mergers, could they also be responsible for the most dominant force shaping the fate of the entire cosmos? This brings us to a theory that connects the enigmatic interiors of black holes with the greatest puzzle in modern cosmology, dark energy. For decades, we've known that the universe's expansion is not slowing down as once expected, but is instead accelerating, driven by a mysterious repulsive force that seems to be woven into the fabric of space itself. We call this force dark energy, and it constitutes about 70% of the universe's total energy content. Yet its origin has remained completely unknown. A startling new proposal suggests the answer might not be found in the empty voids between galaxies, but hidden deep inside the most massive objects within them. What if black holes are not just consumers of matter, but also the primary engines of dark energy? This radical idea centers on a specific property of black holes that has long been taken for granted: their energy content. In Einstein's theory of general relativity, energy and mass are equivalent, as captured by his famous equation, E equals mc squared. When we measure a black hole's mass, we are measuring the total energy of all the stars, gas, and dust that ever fell into it, plus the energy of its own gravitational field. However, this new theory, developed by a team of cosmologists, suggests we've been missing a crucial component. They propose that the intense gravitational energy within a black hole's volume, the energy of the vacuum itself, contributes a form of negative pressure. This isn't the negative pressure of exotic matter in a wormhole, but a fundamental property of the black hole's interior solution in general relativity. In this model, the black hole's total energy isn't just the sum of the matter it swallowed. It also includes this pervasive, repulsive dark energy that is an intrinsic part of its structure. The black hole, in essence, contains a universe of dark energy within its event horizon. The implications of this are profound, offering a potential solution to one of physics' most embarrassing problems, the cosmological constant problem. The cosmological constant is the term Einstein originally inserted into his equations to represent a static universe, and it is the simplest candidate for dark energy. The problem is one of scale. When particle physicists calculate the expected energy of the vacuum from quantum fields, they get a value that is a staggering 120 orders of magnitude too large. This is the worst prediction in the history of science. If their calculation were correct, the repulsive force would have ripped the universe apart before any stars or galaxies could ever form. The fact that we exist means the observed cosmological constant is incredibly tiny, but not zero. The new black hole dark energy theory provides an elegant way to sidestep this catastrophe. Instead of the vacuum energy being a uniform property of all space, it proposes that dark energy is not evenly spread. It is concentrated within black holes. The overall cosmic acceleration we measure is then not a property of empty space, but the collective gravitational effect of all the dark energy stored inside every black hole throughout the universe. This leads to a breathtaking and testable connection between the large and the small. If black holes are the source of dark energy, then the growth of dark energy over cosmic time should be directly linked to the growth of black holes. As the universe evolved, galaxies formed, and supermassive black holes grew in their cores by accreting matter and merging with one another. According to this theory, with every solar mass of material a black hole consumes, its internal store of dark energy increases. The accelerating expansion of the universe isn't a separate, preordained feature of empty space. It is a dynamic consequence of the ongoing feeding and growth of black holes across cosmic history. In this view, black holes are not passive endpoints. They are active participants in cosmic evolution, their growth directly fueling the expansion that will ultimately determine the fate of everything. They are cosmic engines converting accreted matter into the repulsive energy that drives the universe apart. Of course, such a groundbreaking idea faces intense scrutiny and raises challenging questions. Critics point out that this model requires a specific and still debated interpretation of black hole thermodynamics and the nature of the vacuum inside the event horizon. Furthermore, it must be reconciled with the fact that the universe's acceleration began in earnest around 5 billion years ago. Does this theory predict a corresponding surge in black hole growth at that epoch? Astronomers are actively searching for this correlation in the data. The next generation of gravitational wave observatories and galaxy surveys will provide a much more precise census of how black hole masses have evolved over time. If a tight correlation is found between the global history of black hole growth and the measured acceleration of the universe, it would provide powerful, circumstantial evidence that we have finally identified the mysterious source of dark energy, revealing that the key to the cosmos's ultimate fate has been hiding in plain sight within the darkest hearts of its most powerful objects all along. But this concept of a universe birthing new universes through its black holes leads us to an even more radical and mind-warping possibility. What if this isn't just a one-way street, a simple lineage from a parent to a child? What if every single black hole, from the tiniest primordial speck to the supermassive giant at the center of our galaxy, is not merely a gateway but a full-fledged, self-contained cosmos in its own right? This is the ultimate extension of the fecund universe theory, a maximalist vision where our entire reality, with all its hundreds of billions of galaxies, is just one bubble in an infinite, frothing foam of universes, each one nested inside the black holes of a grander parent cosmos. Imagine the structure of this cosmic foam. Our universe exists within it, black holes form. But in this theory, the interior of each black hole is not a crushing singularity or a tunnel to somewhere else. Instead, the moment of its formation, the point of infinite compression, triggers a new Big Bang, inflating an entirely new space-time continuum that is completely disconnected from our own. This new universe will have its own dimensions, its own fundamental constants, and its own laws of physics. The strength of gravity, the mass of an electron, the number of spatial dimensions, all of these could be different. Some of these baby universes might be stillborn, collapsing instantly or expanding into barren, empty voids. Others might be wildly chaotic, with forces so violent that no complex structures can ever form. And a precious few, like our own, might have just the right Goldilocks balance to allow for the formation of galaxies, stars, planets, and life. And within those hospitable universes, new stars will live and die, forming new black holes, each of which itself contains another entire universe, and so on forever. We are not just in a universe that makes black holes. We are, according to this view, inside a black hole that exists within a universe which is itself inside another black hole in an endless, mind-boggling recursion. The philosophical implications of this are enough to keep you up at night, fundamentally challenging our perception of reality and our place within it. It suggests a form of cosmic ecology, an infinite regress of realities without a true beginning or end. There is no ultimate, base-level reality, no foundational cosmos from which all others spring. There is only an endless nesting doll of universes, a fractal structure of existence stretching infinitely in both directions toward the infinitely large parent cosmos and the infinitely small daughter universes. This completely recontextualizes the fine-tuning of our universe, the seemingly perfect calibration of physical constants that allows for our existence would no longer be a bizarre one in a gazillion fluke. Instead, it would be an inevitable outcome of a process that produces an infinite number of universes with every possible set of laws. We don't live in a special universe. We live in one of the countless universes where the conditions are right for us to exist and ask these very questions. This is the ultimate anthropic principle, where observation selects for the conditions of observation from an infinite multiverse of possibilities. From a scientific perspective, this idea, while currently untestable in any direct way, provides a powerful and elegant framework for several deep puzzles. It offers a natural explanation for what happened before the Big Bang, a question that is otherwise meaningless in standard cosmology. In this model, our Big Bang was simply the formation of a black hole in a larger, pre-existing universe. It also provides a potential, purely physical mechanism for the creation of the multiverse, a concept often discussed in cosmology and string theory but lacking a clear origin story. Here, the multiverse isn't an abstract mathematical landscape. It is a dynamic physical structure being constantly generated by the most powerful gravitational engines in existence. The black holes we study are not the end of things, they are the beginning of everything else. While we may never be able to peer into another universe to confirm this theory, its profound beauty lies in how it connects the physics of the very large with the mystery of our own origins, suggesting that the key to understanding where we came from is hidden in the darkest, most mysterious objects our universe has to offer. Up until now, we've seen black holes as ultimate consumers, taking in matter and energy and giving back almost nothing in return. But what if we could turn that logic on its head? What if a black hole, specifically a spinning one, could be used as the most powerful battery in the universe? This brings us to a brilliant and audacious idea known as the Penrose process, a method that, in pure theory, would allow us to steal energy directly from a black hole's rotation. The key to this cosmic heist lies not within the event horizon, but in a strange, surrounding region of twisted spacetime called the ergosphere. In a non-spinning black hole, the event horizon is a simple, spherical point of no return. But when a black hole rotates, described by the Kerr solution, its spin drags the very fabric of spacetime around with it, like a whirlpool in water. This effect creates a flattened, oblate region outside the event horizon, the ergosphere, where it becomes impossible for anything to remain stationary. No matter how powerful your rockets, you would be forced to move in the direction of the black hole's spin, caught in this cosmic current. It is within this turbulent zone that Roger Penrose, in 1969, realized a remarkable loophole in the laws of physics existed. Imagine an advanced civilization sending a payload, perhaps a large capsule, into the ergosphere. Once inside, the capsule executes a carefully calculated maneuver. It splits into two pieces. This is not a simple separation. It's a precisely engineered theft of rotational energy. One piece of the capsule is directed on a trajectory that sends it crashing past the event horizon into the black hole. The other piece is flung back out, escaping the ergosphere entirely. The magic lies in the fate of the two fragments. The piece that falls into the black hole is deliberately given a negative energy orbit relative to the distant universe. This doesn't mean it has negative mass in the conventional sense, but that its trajectory, when calculated from far away, results in it carrying less energy than if it had simply been at rest in the void. To conserve the total energy of the system, the other fragment must carry away more energy than the original whole capsule possessed when it entered. In essence, the infalling piece robs the black hole of a tiny portion of its rotational energy, and that stolen energy is gifted to the escaping fragment. The black hole itself pays the price, slowing down its spin by an imperceptible amount to balance the cosmic books. The science fiction potential of such a mechanism is staggering to contemplate. A civilization could, in principle, construct a black hole power plant. They would not be burning fuel, but actively harvesting the rotational inertia of a spinning singularity. They could send automated probes into the ergosphere, programmed to split and redirect, with the energy-rich fragments being collected by a station in a stable orbit. The energy output would be on a scale we can barely imagine, potentially providing power for interstellar travel, mega-structures, or computations of incomprehensible complexity. Unlike a star which eventually burns out, a stellar mass black hole's rotational energy is a vast reservoir that could be tapped for billions of years. This isn't just another power source, it would be the ultimate achievement in energy engineering, turning the most destructive object in nature into a cosmic dynamo. However, the leap from theoretical possibility to practical application is a chasm wider than the black hole itself. The engineering challenges are so immense that the Penrose process remains, for now, a profound thought experiment. First, there is the sheer precision required. The initial trajectory into the ergosphere, the timing and mechanics of the split, and the escape path for the energy-rich fragment would have to be calculated with an accuracy far beyond our current capabilities. A single error of a fraction of a degree would send both pieces careening into the event horizon, resulting in a total loss. Second, the energy gains, while positive, might be relatively modest for the incredible risk and effort involved. The process is not 100% efficient, and the energy we could extract from a single maneuver would be a tiny fraction of the black hole's total rotational energy. To make a meaningful impact, you would need to perform this delicate operation millions of times, a relentless, automated mining operation in one of the most hostile environments imaginable. Furthermore, the environment itself is a deal breaker. The ergosphere of a realistic black hole would not be a clean, empty void. It would be a maelstrom of intense radiation, searing heat from the accretion disk, and powerful tidal forces that would threaten to tear any complex machinery apart. The black hole would likely be surrounded by a magnetosphere of unimaginable strength, generating unpredictable and lethal electrical currents. And then there is the simple problem of distance. The nearest black hole we know of is thousands of light-years away. Transporting the infrastructure to build and maintain such a facility across interstellar space is a hurdle that dwarfs the physics of the extraction process itself. So, while the Penrose process stands as a testament to the genius of theoretical physics, revealing that even a black hole's energy is not entirely locked away, it also serves as a humbling reminder of the gulf between a beautiful equation and a working machine. It shows us that the universe may be filled with possibilities, but it rarely makes them easy. And so, after this incredible journey through cosmic gateways, primordial relics, and holographic realities, we arrive at the final, and perhaps most profound, theory on our list, a concept that isn't just one more idea, but the grand culmination of them all. This is the belief that black holes are not merely fascinating objects to study. They are the ultimate key, the Rosetta Stone that will finally allow us to unify the two great pillars of modern physics, Einstein's general relativity and the quantum mechanics. For over a century, these two frameworks have existed in an uneasy truce. General relativity gives us a magnificent, geometric description of the cosmos on the largest scales, painting a picture of planets, stars, and galaxies moving through a curved spacetime. It's the theory of the force of gravity. Quantum mechanics, on the other hand, gives us an equally powerful, though bizarre, rulebook for the subatomic world, explaining the behavior of particles and the other three fundamental forces, electromagnetism and the strong and weak nuclear forces. The problem is, these two rulebooks are written in completely different languages, and they utterly fail when forced to meet. Nowhere is this conflict more stark and unavoidable than at the edge of a black hole. The event horizon is the precise battleground where the smooth, deterministic fabric of spacetime described by general relativity directly confronts the fuzzy, probabilistic, and particle-based world of quantum theory. It's the place where our current laws of physics break down and plead for a deeper, more complete understanding. This is why solving the mysteries of black holes isn't just an academic curiosity. It is the essential pathway to what physicists call a theory of everything. This would be a single, coherent framework capable of describing all physical phenomena in the universe, from the frantic dance of quarks to the majestic swirl of galactic superclusters. It's the holy grail of modern physics, and black holes are the guardians of that grail, presenting us with puzzles that any candidate theory must be able to solve. Take the black hole information paradox, which we explored earlier. This isn't just an obscure debate, it's a fundamental test of logical consistency. A successful theory of quantum gravity must be able to tell us unequivocally what happens to the information of an object that falls in. Does it get destroyed, forever violating quantum law? Is it preserved on the horizon, as the holographic principle suggests, or is it slowly leaked back out via Hawking radiation? The correct answer will immediately rule out entire classes of theories and point us toward the right one. Similarly, the true nature of the black hole's center, whether it's a true singularity, a Planck star, or a fuzzball, is another critical benchmark. Our current equations give us an infinity at the center, and in physics, an infinity is usually a sign that you're missing a crucial piece of the puzzle. A theory of everything must be able to describe that central point without breaking down, seamlessly blending the quantum nature of matter with the gravitational warping of space. This quest has already given rise to several brilliant, though still unproven, candidates. String theory, for instance, proposes that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating strings. The different modes of vibration correspond to different particles and forces. In this framework, the paradoxes of black holes can be approached by reimagining them as fuzzballs, dense, tangled knots of these fundamental strings, with no sharp event horizon or singularity, thereby naturally preserving information. Another leading contender is loop quantum gravity, which suggests that space itself is not smooth and continuous, but is woven from a network of discrete, finite loops. In this theory, the intense collapse of a star doesn't lead to an infinitely dense point, but reaches a maximum density and then rebounds, potentially creating the very white fountains or Planck stars we discussed. Both of these theories and others use black holes as their primary testing ground. The calculations are immensely complex, but the goal is clear: to find a mathematical structure that can accurately predict what we see, or will one day see, when we look at these cosmic enigmas. Achieving this unification would be one of the greatest intellectual triumphs in human history. It would be the moment we finally grasp the fundamental software the universe is running on. It would allow us to peer back to the very first moments of the Big Bang, a time when the entire cosmos was in a state similar to the interior of a black hole. It could unlock a deeper understanding of the very fabric of reality, potentially revealing new dimensions of space or the underlying reason for the values of nature's constants. This isn't just about completing a textbook, it's about rewriting it from the very first page. Every strange theory we've explored today, from black holes as universe generators to their potential role as dark energy engines, represents a different piece of this grand puzzle. They are all glimpses from different angles of a deeper truth that we are only just beginning to apprehend. The path forward is steep, and the answers are hidden behind the most formidable barriers in nature, but the pursuit is perhaps the most noble and profound endeavor we can undertake: to fully understand the cosmos we call home, and in doing so, to finally understand the fundamental rules that brought it and us into being. And so, we have journeyed together across the event horizon of the known, venturing into a realm of breathtaking possibilities where the universe is far stranger and more magnificent than we ever dreamed. We began by shattering the classic image of the black hole as a simple, destructive pit, discovering instead a landscape rich with potential. We explored the idea of a singularity-free core, where a Planck star or a gravastar might replace the infinite, preserving the logical consistency of the cosmos. We considered the black hole not as a final grave, but as one half of a cosmic circuit, a gateway to a white hole, a transient fountain of creation, or even a tunnel through a wormhole to another time or place. We then scaled these ideas to their most profound implications, contemplating the theory that every black hole is a cosmic womb, birthing an entirely new universe with its own laws of physics, a concept that transforms the multiverse into a dynamic, evolving ecosystem. We grappled with the slow, inexorable evaporation of black holes through Hawking radiation, a quantum whisper that ensures even these titans are not eternal. This led us directly into the heart of the fierce battle between quantum mechanics and general relativity, the black hole information paradox, and the radical solutions proposed to resolve it, from the destructive fury of a firewall to the elegant, mind-bending storage of all information on a two-dimensional holographic surface. Our exploration took us to the frontiers of dark matter, where ancient primordial black holes could be the invisible ghost shaping the cosmos, and to the edges of survival, where one could theoretically cross the horizon of a supermassive black hole and witness the end of time. We entertain the possibility of dark planets orbiting these dark suns, and we even dared to connect the cosmos to consciousness itself, finding a tantalizing analogy in the way both a black hole and a brain might process information. We saw how black holes can be kicked clear out of their galaxies by their own violent mergers, and how their spin might one day be harnessed as the ultimate power source. We confronted the terrifying prospect of a naked singularity, an uncloaked point of infinite lawlessness, and finally, we considered the staggering proposal that the dark energy accelerating the universe's expansion might not be a property of empty space, but is instead generated and stored within the hearts of black holes themselves. This incredible voyage through 25 theories reveals one unifying, transformative truth. Black holes are not the monstrous endpoints of physics we once feared. They are the universe's most brilliant teachers, its most extreme laboratories, and quite possibly the very key to unlocking a final, unified theory of everything. They force us to question our most basic assumptions about space, time, matter, and information. They are the crossroads where gravity and quantum mechanics meet, and by studying them, we are not just learning about distant cosmic objects, we are deciphering the fundamental source code of reality. The conversation does not end here, it is only just beginning. The universe is a story that is still being written, and you are a part of it, so we turn the microphone over to you. Which of these theories completely reshaped your understanding of the cosmos? Was it the holographic principle suggesting our reality is a projection? The idea that we might be living inside a black hole in a grand, nested multiverse? Or the sheer, explosive potential of a black hole's final transformation into a white fountain? Let us know in the comments below. We are genuinely excited to read your thoughts and continue this cosmic discussion together. If this journey into the unknown expanded your mind, if you enjoyed staring into the abyss and finding that it stared back with infinite possibilities, then please give this video a like. It truly helps us continue creating these deep dives into the wonders of the universe, and to make sure you never miss our next adventure, whether it's into the mysteries of quantum fields, the enigmas of dark matter, or the next great discovery about black holes, hit that subscribe button and ring the notification bell. There are endless mysteries waiting for us just beyond the horizon, and we can't wait to explore them with you. Thank you for watching and keep looking up.